You can't hear me. Can hear now?
I can't hear you, sir.
Hey, how come?
I can't hear anything.
Can't hear anything. What is wrong?
I can't hear anything.
Let me see what is wrong. What is wrong? What is wrong?
Hello, sir.
Yeah, still cannot hear. Still cannot hear. Let me start a new Zoom then.
Oh. Hello?
Yeah.
Okay, now I can hear.
Can hear.
Yeah.
Okay. I thought what is wrong, going to start a new Zoom already. Okay. So you want me to go over diffraction lah? Am I right?
Right, but then the past year first lah, sir.
Past year first okay lah.
Got time, then go to lah.
Okay. Hey, how come so many wave optic? Okay, can see the screen. 23 wave optic, past year question. Let me know if you cannot see.
I can see.
And see, okay. Okay. Let's survey. Wave optics. Diffraction by a single slit is popular, and so is polarization. Polarization and diffraction from a single slit. Others does come out lah, but not that consistent lah. Okay. Know what is wavefront? Know what is Huygens principle? Right? Know what is coherent? Know the definition of reflective index, speed of light over the speed in the air over speed in the medium, and then know what is optical path. Right? Reflective index times the length that pass through the medium. Then if you have the path difference between original wave in air and one passing through a medium or reflective index, T is just your path difference is n minus 1 whole thing T. I can derive it or memorize it. Right? Condition for two slit interference. Both waves must be of the same type. That means sound wave and sound wave meet at a point. They must meet before they can interfere. Same direction of polarization. And then let me just adjust the screen a little bit. Okay, for the path difference, for constructive interference, memorize that. For destructive interference, is n minus half, floating lambda, and there's no zero there. It's 1, 2, 3. Right? Path difference is the extra distance which a wave travel compared with the other. Then interference, when two or more waves meet at a point, there is a change in overall intensity or displacement. Right? How do we know there's interference? When the wave meet, we see a change in overall intensity or displacement. Right? This formula for intensity you need to remember to explain the observation. And then this is the formula for the fringe separation. X is your fringe separation. And then usually they will probably use arc length, right? Arc length, this is the radius, right? The trick, and theta, the angle. So that formula is derived from arc length and then using this formula, right? For xm, for the nth fringe, right? M is there. Then for interference in the thin film, right? The key to remember is there is a 180 degrees change on reflection occur when light incident from a less dense medium to a more dense medium, right? And then remember the path difference is it move in if there's your thin film. If this is your T, so it move in T, NT, and then NT back. That's why you get 2NT. And then this one is it's best not to memorize too many things, know how to derive. Derive from here, 2NT. And then this one is because of that, right? 180 degrees change in phase. For non-reflective coating, it's more popular. Right? Just memorize it. Right? It's 2NT. Right? If there's a thin film, it's going NT, that's why it's 2NT. And then for destructive interference, it's lambda over 2. Okay, now to derive the transmitted, right? They are just opposite to the reflection. Okay, that one there. Then now for your diffraction of single slit, right? Basically, we take a point here and then one at the midpoint. We want destructive interference, not constructive, destructive interference. So there's a phase difference between this point and that point, or a path difference, path difference of between this length and this length of lambda over 2, and then we derive this equation. Right? If we circular aperture, it's very small. That's why we round it off to lambda over A. Okay. Circular aperture, we use 1/22 lah. And usually we use arc length lah. Right? There's your D. That's your theta. Theta mean S is your arc length. That distance there. And we call Y. Okay. And now resolution. Right? Resolving power. Now what's resolving power? Now it's Rayleigh criteria. Right? That's your resolving power. And that's the graph for diffraction. Remember that this is the widest. The central band is widest. Intensity are different. Right? That's the two key. Central band is larger compared to the other band, not by interference pattern. And then the intensity also the largest at the central band. These are smaller. Right? So these are all the formulas that you need to remember. Diffraction grating, d sine theta is m lambda, or sine theta is nm lambda. Right? M is that. Maximum number of spectral line, 2m plus 1. Right? This is your slit spacing. N is the number of lines per.
Just the phone.
Say again.
Teacher.
This is the distance between the line, or distance between the slit spacing. N is the number of lines. Usually it's given as per cm or per millimeter. Right? Maximum, you just remember that equation. Put your sine theta equals to 1, that's all. And for polarization, right? usually the polarizer, usually we represent one vertical, one horizontal. And the polarizer allow only one component to pass through. So this is your I naught. So I naught is just your 2I1. Right? This I1. Sorry, this I. This I1. The final one. So I naught is 2I. So if that is your I naught, right? Remember this is polarized. Right? It's polarized. I naught. Then this is I1. So I1 is related. This is the angle. So it's I naught cos square theta. And then for polarization on glass or glass block, right? Bruce law, that's your Bruce law, where your tangent P is your angle of incidence. Tangent P equals to your reflective index of glass. Then your optical guide, optical fiber or fiber optic, right? That's the coating, that's the core, that's the cladding. Remember this formula. Light travels through the core of the optic fiber by bouncing from the cladding and total internal reflection. And the key to remember is that that angle must be greater than the critical angle for total internal reflection to occur. And then this is N1. N1 is this one. N2 is the cladding, reflective index of cladding. So reflective index of the core is greater than the reflective index of cladding. And then theta 1 must be greater than C. Okay, what is the answer for this one? Two source emit waves which interfere in a region which condition is not necessary for stable interference pattern to occur. Stable means we can see. If it's not stable, we cannot see. It changes with time.
Boy,
The wavelength of both must be equal, necessary. The frequency of both wavelength must be equal. That's a condition for coherent. The amplitude of both wave must be equal. Not necessary for amplitude to be the same. This condition is required if you want destructive interference only. The type of both wave must be similar, right? They must be the same, necessary. So the answer is C. They can interfere whether their amplitude is the same or not. But if you want to have a destructive interference like dark band, then you must have amplitude the same. Then they will destroy each other completely. Which light source is incoherent?
C, teacher.
Which light source is incoherent? Light source from diffraction grating. Coherent source have constant phase difference. It means that the source have the same frequency or wavelength. B. Light of the same frequency from two separate sources. Okay.
Teacher, but they said same frequency ones. Oh, okay. So
Is it
why C cannot answer?
which light source is incoherent? Light that is partially reflected from the front and back layer of a thin film. This is coherent. right? The thin film going in, they have the same frequency. They have the same frequency. That's why they can interfere. They are from the same source. That's why they have the same wavelength. Can or not?
Okay.
Okay or not?
Hmm.
Can. The interference fringes produced by Young's two-slit experiment is shown in the diagram below. If the distance between the two slits is increased, which diagram shows the coherent interference fringes?
Correct.
Which one? Which is the answer?
Donkey je.
Why donkey?
I mean, two slits, so it's going to increase more and more, and they separate more lah.
Right? You just use that. That's your distance x from center to center. That formula. So you decrease this one. Sorry. You increase this one. So you decrease the x. So that distance from center to center must decrease. That's how you reason out. Okay. Donkey, okay, good. Can see quite popular there. A solar cell consists of silicon. Okay, it's a silicon with a coating of silicon oxide. That's a silicon oxide shown in the diagram below. If the reflective index of silicon and silicon oxide given there, they are very kind to you. What is the minimum thickness? That thickness there, T of the coating, so that the monochromatic light of wavelength 600 nanometer is not reflected from the surface of the coating. So you want destructive interference to occur. What is the formula to use? Yep. All this should have been done at home.
Two and t equals to m plus 1/2 lambda.
Usually we just use your m equals to 1 now. Right? Don't bother about the other higher order. Non-reflective coating. Right? 2nt, nt is going down, path different, going up, path different, nt, that's why it's 2nt. Destructive interference half lambda. And put in your value. You want t, take your 2n down. So it's 4n. 4n is 2. That's your n. Not this one, this one. The coating. And calculate out. Boy. Okay. Anything not agree? If okay, let's go to number 5.
Go back.
Go back. Just memorize this formula, that's all.
Oh, it's a fixed formula.
Yeah. It's easy to remember. You want destructive interference must be half lambda. Then path different, nt, going up, nt. So it's 2nt.
That means the n is 2, not 3.5.
No, we don't use this one. This is the coating. The path difference is in the coating, not the silicon. In the coating, that's why it travel in the coating. Come down, reflected back, and interference occur at the surface here.
Is in the one you said coating.
The coating is silicon oxide, this layer. Non-reflective coating. Okay.
Okay.
No, this layer, not the silicon. Silicon oxide is the coating that we want. A thin film A thin transparent coating or reflective index 1.25 is deposited on a length of reflective index 1.5 to reduce refraction. What is the minimum thickness of the coating so that the normal incident light of 550 nanometer undergo destructive interference after reflection from the lens? Is the same. Yeah, more reflective coating, same formula used, put in your value, that's all. You use nanometer, get nanometer, then convert it to meter, that's all. 10 to the power minus 9 to 10 to the power minus 7. So answer is B. Okay.
Oh,
What's the answer for this one?
so go back to. So the trick is you must know which one coating and not coating and substitute
Yeah, you
the
must know
coating
which
only.
coating. The coating is the top layer,
Okay.
right? So it's usually the smaller one they use, not the bigger one. The intensity distribution of a diffraction pattern produced on the screen when monochromatic light with wavelength lambda is incident on a single slit of width A is shown in the diagram below, which graph represents the intensity distribution when the slit is replaced with a slit of 2A. Yep. What is the answer?
C, teacher.
Okay. Right? We just assume that the intensity I naught, that maximum intensity, is proportional to A square. A is the slit aperture. Okay, so that is the new one over the old one. Right? It's directly proportional. So this A2 square over A1 square, and put in your value. I1 becomes I naught. That's your I naught. And A2 becomes 2A. That's your 2A. A1 is just your A. It's 4 times. That's your 4 times. Right? Just replace your A with 2A. That's all. That's why we get this one. Okay. So answer is C, correct?
Go back, Joe. Okay.
When monochromatic light is incident normally on a narrow slit, a diffraction pattern is formed on the screen. Which statement is true of the diffraction pattern if the slit is narrower?
A, teacher.
Right? For the first minimum, you go to the formula to reason it out. Narrower, A is narrower, that means A is smaller. Sin theta increases. Okay, good. A.
1 minute, Joe.
Yeah. Okay.
Wait, Joe. Okay.
Monochromatic light incident on a single slit of width A. Secondary sources A1 and A2 emit wavelets that meet at P on the screen. Which diagram shows the correct path difference between two wavelets to produce the first minimum of the diffraction pattern on the point P? Okay.
Okay. A, teacher.
No. Usually we take half A. Right? We want disruptive interference. So a wavelet from here and a wavelet from half A destroy each other. And then other wavelet below and other wavelet below that also destroy each other. That's why it must be lambda. Okay.
Okay.
Anything not clear? The disruptive interference, the path difference between the two rays or wavelet, one from the
So
upper.
can you explain this again, Acha? I don't understand.
There, we use this one.
Okay.
We take half A here. So we take a point here and a point here. Right?
Okay.
Point just below the A and a point at half A. So you want it to be disruptive interference. So it's half lambda. Lo. So after that, we take another point below, same another point below, also half lambda. So this is half lambda. Path difference between this length and that length is half lambda. So that must be full lambda. Okay?
Okay.
I just want to trick you only, see whether you understand your physics or not. The area view of a single slit diffraction experiment set up using laser light of a certain wavelength is shown in the diagram below. The width of the central fringe will be smaller if the width of the central fringe smaller if
the boy.
Right? Go to the formula to argue it out. You want sorry, this one is disturbing.
Width to be smaller, so the A is to be smaller.
A is smaller, that will be larger. So the width of the central.
So answer is A. Sorry, A. Answer is A.
Right? The width of the central fringe will be smaller. You look at theta. You want theta to be smaller. Right? For sine theta to be smaller, lambda needs to be smaller, or A needs to be larger. The answer is B. Okay.
1 minute, sir. Okay.
Parallel line of wavelength 590 nanometer is incident normally on the diffraction grating. The first order maximum is observed at 30 degrees. What is the grating separation? You want to find donkey D. What's the answer? Yeah.
Sir, this one I'm not sure, sir.
Just use this formula only. That's all. Straightforward. Want to find D. Put in your value. Take your sine theta down. Right? 30. That's your 30. That one changes to meter. Your M equals to 1. Calculate out. Okay, in fact, you don't need to change to meter. You can use nanometer, then the answer will be straight away nanometer rather than, right? Answer is C. Rather than wasting and set, calculate, wasting to recalculate again. Right? If it is nanometer, okay, you don't need to change that to meter. Unnecessary. Okay.
Okay.
Beam of non-polarized light passes through polarizer. The angle between the polarizing axis of the polarizer is 30 degrees. What is the percentage of intensity of the non-polarized incident beam which is absorbed by the two polarizer when the light passes through the two polarizer? Okay. What's the answer?
C, teacher.
Right? Understand that this is a polarizer. So this is I0, this is I1, and use the equation. I1 is just I0 cos square theta. So I0, if this is I0 is just half I. Then replace your I0 here with half I. Fraction transmitted. Right? This is transmitted. So you just take your I, this one I down. That's your fraction transmitted. Is half cos square theta. Then you want right? This is 37.5%. You want percentage, you times 100, that's all. So percentage as well is 100 minus this one. No? Okay. See? Anything not clear?
You can explain again, Archer.
Okay. Remember, this formula is for the one coming out here. This is your I0. This is your I. So your I0 is half this I. That's what we get here. Right? The purpose of this polarizer is to, usually we remove one component. One component is vertical, one horizontal. So this one allowed the vertical to pass through, which is I0. That's why we have half I, half I. Then using this equation, Bruce law, replace that I0 there. Right? Replace I0 with half I. So this is the one that's transmitted. Percentage transmitted, you compare to the original I, take the I down. So that's, you want percentage, you times 100. So it's 37.5 is the percentage transmitted. Absorb 100 minus 37.5, I get 62.5. Yep, which part is not clear?
Okay, teacher.
Quite popular. You don't know, I better learn that. Two polarizer P1, P2 with their axis of polarization parallel to each other are shown in the diagram below. P1 is illuminated with unpolarized light of intensity I0. This is your I0, unpolarized. Through what angle must P2 be rotated so that the intensity of light emerging from P2 is 0.22 I0? Right? Remember, what is the answer?
Answer A.
Okay, let's see. Remember, we are just using different symbol, that's all. This is called I0, but we call I0 here. But you must know how to change all that. Okay. Right? That formula is for this diagram. That's your I naught. And there's your I1 coming out. So in this case, your what did I do? Oh, I using this formula. I hope you can see that. This is your I naught. So coming out of this one is half I naught. Right? Half I naught. So that's why I got half I naught. So I1 is the one coming out here. Let me see. Answer is A. Can or not? Which part you are not clear?
Teacher, why I not over 2?
Okay. This formula is for this diagram. Okay. So I1 is the same as I1 coming out here. So in this case, I want this I naught. Right? This I naught is this one. So this I naught is half I naught, no? This one. Cannot.
Okay.
You must know how to play with the symbol. Half of this I naught will pass through. This is your I naught. Half of that. That's why I use that. And then this I1, the Y1 coming out, is the one given here. That's I1. I know can cancel off. Then I just take the square root of that and take the inverse of cos. Okay,
Okay.
you can see quite popular. Plane polarized light beam with intensity I naught pass through a polaroid. The angle between the transmission axis of the polaroid and the plane of polarization is theta, which expression shows the correct intensity of light I passing through the polaroid. Yep. Same as previous one. What's your answer? Same. Use this diagram. Remember this diagram? Right? That formula. Except that the I naught is here, not this one. They use I naught here. So if the amplitude is A naught, then I is proportional to amplitude square. I naught is proportional to amplitude square. Final amplitude A equals to A naught cos theta. I is proportional to A square. I is proportional to A naught cos theta. Right? A naught cos theta is I naught cos square theta. B. Okay. Basically derivation only, not much.
Okay.
So it's exactly this equation. That's all. Here's your eye passing through there. So they just change the symbol, that's all.
Okay, sir.
An optical fiber is a physical structure usually made of plastic or glass, which is able to transmit light through it. Which statement is not true about the optical fiber? Yep.
Where are you?
A is true.
C. The answer is C.
Optical fiber are used in telecommunication and medical diagnostic. True.
True.
Optical fiber used in total internal reflection transmit the light through it. True. Optical fiber
C
cause
no.
almost no loss in intensity when light is transmitted through it. That is correct.
Okay.
Right? There's no air. You pass current through a wire, there's I square R loss. But I pass through light through the glass, there's literally nothing lost. Very little loss. Only the impurities will cause the loss, that's all. So
Only
that's
the
why
what, sir?
glass doesn't have any resistance. When you pass current through a wire, the power loss is I square R. But optical fiber, no. You just pass light through it, that's all. So very little is lost. Optical fiber consists of transparent film surrounded by a layer of higher reflective index. No, it should be, the core should be higher reflective index. Okay, donkey is the wrong one. Okay,
Okay.
reflective index of core must be greater than the cladding for total internal reflection to occur. Sorry, for total internal reflection. Okay, next one, number 15.
Number 15, boy.
Which one is not true? The inner core is made of metal. It's not made of metal. They are made of glass.
Sorry. A.
Right? The inner core is denser, correct? The angle of incidence is greater than the critical angle. Right? The angle of incidence is greater than critical angle. True. The light ray in the inner core undergoes total internal reflection. That's what we want. True. The answer is A is the wrong one. Okay, this topic not every year come out. Either in A or B, we compare the two together. If it doesn't come out A, we come out B, but it doesn't come out every year. But if it does come out, what are the common area? It looks like two slit interference pattern. No? Okay, let's go over that. State two conditions to obtain interference pattern. What are the conditions? Yep. Two waves must cross, same type, same speed, coherent. same amplitude. If you want to see for light, bright and dark, then you must have same amplitude. Okay.
Okay.
Light source S is placed at the axis of S1 and S2. The source is then moved away from the axis as shown in the diagram below. In both cases, A and B, right, there's your A, there's your B. S1 and S2 act as coherent sources. State the condition for interference pattern form. Yeah, for A, what is the condition to have interference pattern? You're not ready yet. For A, formation of bright fringes, the path difference is n lambda. This must be from the same wavefront. S1, S2 must be from the same wavefront. Okay, for S, so the interference pattern will occur at n lambda, where n 0, 1, 2, 3, 1, 2, 3, and so on. And for B, we can see that is this S1 from different wavefront. This is the second wavefront, but the two wavefront path difference is lambda. For B, the formation of bright fringes, the path difference equals to n plus 1. Right? That's a difference of wavelength, one wavelength. That's why we add 1 in, right? 1 lambda. N is the same, 0, 1, 2, 3. Okay.
Okay.
Right? This is the first wavefront. This is the second wavefront. There's a difference. That's why we add the 1 here. In A, a monochromatic light of wavelength 590 nanometer is used. The distance between S1 and S2 is given. If the screen is placed 1.2 meter from S1 and S2, interference fringes are observed. Calculate the distance of the fourth bright fringe and the central bright fringe. Yep, what formula to use? What formula should I use? Right, that formula? Xn or Xm? If you use M here, then this will be M. If you N here, then this will be N. And put in your formula. Right? N is 4, the fourth one. And this is nanometer, change it to meter. And 1.2 meter, 2 meter. And then that is your D. Right? Change it to meter. Right? Your answer should be meter. So I give my answer as a millimeter. Okay. Any comment? Anything not clear?
Clear, sir.
Okay. State the principle that explain diffraction.
Huygens's principle.
Yeah. A monochromatic light with frequency 6 10 to the power 14 Hz is incident normally on the diffraction grating which is 300 lines per millimeter. Determine the angle of diffraction for the second order maximum. Okay, what formula to use? Yep, what's the formula?
The formula, d sine theta equals to m lambda.
Okay, good. D sine theta, or you can use, since it's given in lines, instead of putting the D here, you can put the M here.
They change it to 1 over n. Yeah.
And put in your value. Lo. Right? Your N is 300 or 1 millimeter. 1 millimeter is 10 to the power minus 3 meter. Right? You have to change that to meter. And your M is the second order, 2. It just make life difficult for you. That's the speed of light, C over frequency to get wavelength. That's your C, that's your frequency. Calculate out. 17.5. Can?
Okay. Go back. Okay.
Determine the number of maximum produced.
2m plus 1.
Yeah. Determine what's the answer?
5. Oh. Teacher, why sine theta equals to 1?
You want maximum number?
If minimum means?
No minimum. Where got minimum? The widest you can go. You cannot go over 90. So that's why you use theta is 90 degrees. Just sine 90 is 1. No?
Okay. Okay, Jeff.
Yep. I think this one is a bit messy lah. You get a bit confused. Number of maximum, number of line, maximum line, number of maximum. So this one they want M rather than 2M plus 1. State Huygens principle. That one is a memory work. Every point on the wavefront can act as a secondary point source of wave. The wave from the secondary point source are called wavelet. The new wavefront is constructed by drawing a line touching all the wavelet. A monochromatic light of wavelength 633 nanometer is incident perpendicularly onto a pair of slits. The separation of the slit is 12 micrometer. A series of bright and dark fringes are formed on the screen, located 2.8 meter from the slits. Based on Huygens principle, sketch the diagram to show the formation of wavefront which produce bright fringes on the screen. Okay. Yep, that's what you should get. Firstly, produce a spherical wave. And these are the two wavefront. You just have to bring your compass along. Look. And then just draw a circle. Okay or not? Anything not clear? They give for all the construction. Calculate the distance between the two adjacent bright and dark fringes on the screen. Right? Use your formula. Put in your value. Change it to meter. Your donkey. Capital D, that's your donkey. That D is that one. Change it to meter. Calculate out. 0.48 meter. there's a possibility you may have to divide this by 2 because they want bright and dark fringes. Okay. Okay with that? Any comment? Any comment? Any comment? Okay or not? Anything that is not clear? X is the distance between bright fringes. That means from center of bright fringes to center of bright fringes. That's your X. But here he want from bright and dark to center, lor. That's why he divide by 2. Lor. What happened to the fringe width when a shorter wavelength monochromatic source is used? Yep. Yep. What happened to X when you have a shorter wavelength?
Don't know, sir.
Just using this formula only. Okay, shorter wavelength. X is smaller.
Shorter wavelength means then you'll increase.
The
Decrease.
between the fringes decreases when a shorter wavelength is used, as X is proportional to your wavelength. That's all. What's the problem?
No. Okay, continue, sir.
Describe the change in the fringe pattern if the beam from one slit has a phase shift by half a wavelength relative to the beam from the other slit. Okay. What will happen?
Don't know, sir.
Right? If the beam from one slit is shifted by half a wavelength, the interference pattern would be similar. What's the difference? Except where there is bright, now it is dark. That means the center fringe would not be dark, not bright as previously. Where there's bright, now it is dark. And where it is dark, the dark fringe is now bright. The center fringe is dark, the fringe spacing remains the same. Okay? Explain the change in interference pattern if the experiment is carried out in water. Yeah, I still remember when I was your age, I struggled with this one. That time we were using Nelson and Parker also. Right? Application question, apply your knowledge. What will happen? Can? If the experiment is carried out in water, the wavelength becomes shorter. Okay, compared to air, now the wavelength becomes shorter in water, and then X is proportional to wavelength. The fringe width becomes smaller. We are just using that equation, that's all. That equation. If this one's smaller, that one will be smaller. The fringe width becomes smaller and the number of fringes increases. Okay.
Okay.
Describe with the aid of diagram the formation of young double slit interference fringes. That's all. Right? Quite popular. And make sure you bring your compass along. Derive the formula for the fringe separation X for the monochromatic light of wavelength lambda if the separation of slit is A and the distance between the slit and the screen D, assuming that D is very much greater than A. Okay, so since it's 3 marks, we start drawing, just explain. No? You say describe with the aid of diagram the formation of Young's double slit interference. Each of the two slits behave as point source. This slit there and this slit are point source or wave, are coherent sources emitting circular waves. The circular wave from both slits interfere to produce region of constructive interference where the crust of both waves superimpose given bright fringes, and destructive interference where the trough meets the crust giving a dark fringe. Number 2, remember the 180 degrees phase change on refraction occur when light incident from a less dense. What am I doing? This one is derive a formula for fringe separation X of monochromatic light of wavelength lambda if the separation of the slit. What am I doing? What am I doing? No, this one is not required. This one is not required. What am I doing? This one is not required. Sorry. They on the derive, that's all. So you remember your derivation, no? Right? So remember, we are just using this triangle and this triangle, which is this one. Just explain your S1, S2 are your slits. That's your XM, right? N maximum, that's the central maximum. S1P equals to NP. S1, what am I doing?
After this can stop here. The question 2, question 3, 2 tomorrow.
I think question 2, I let you derivation. That is your S1P, and then NP is the same. So that is your path difference. Right? Path difference is just your M lambda. This is your D. So D sine theta is this one. That's what we are doing. So we can find 1 sine theta, take your D down. That's why we get the equation. Right? We're just using this triangle. That's all. Refer to your note there if you want. Then after that, we use this triangle. Right? Tangent XM over D tangent theta. And since this is small angle, sine theta equals tangent theta. Okay, so these two are equal. That's how we get our equation. So for m bright free, we replace this one by m1 plus 1. That's all. And then subtract to get your x. That's your x. Okay, distance between fringes. Distance between bright fringes. I think we will leave it for tomorrow lah. If we got the time. Rather than carry on, I think you're too tired already. You still go to school?
Yes, Chair.
I thought you should stay back and study already, since your exam is next week. If you are benefiting.
Yeah, but then they told me go to school because I know I won't study in the house.
Well, if you find it beneficial, then go. Lo. If you find it don't gain anything, then stay at home to study. Lo. Okay.
Yeah.
So we'll stop here. Since you are too tired.
Okay, thank you, Chair. Thank
See
you,
you
Chair.
tomorrow. See you tomorrow at same time, 3:30.
Okay, Chair. Thank you, Chair.
Okay, bye-bye.
Bye-bye. Bye.